I'll go in for warning for unimproved message.
Okay, so it's time to go ahead and begin. So today's lecture, there's going to be a couple of new topics, but within those new topics, we're going to be reviewing quite a bit of what we've already discussed this quarter. So, I think this is a really good class because, like I said, there's some new stuff, but within that new stuff, there's stuff we've already talked about. So it's also sort of a review of a lot of what we talked about up to this point in the class. So first, we're going to talk about universal gates, okay, what's meant by that term. And then you're going to see the use of them. And as I have up on the board here, there's two of the gates that we've talked about are universal gates, the NAND gate and the NOR gate. So I'm going to, again, explain what's meant by universal gate and then show you some examples of how it's used with the NAND here in class. And then part of the activity today is basically what I show you with the NAND, I want you to do with the NOR, which is the other. Okay. And then we're going to talk about SOP to another digital form, which is NAND, and also POS to another digital form, NOR. And the activity basically has two parts. The first part is, like I said previously, doing what I show you with the NAND using the NOR. And then the other part of the activity is getting some practice with these two additional digital forms, NOR and NAND. And then after the lecture and activity, you'll be able to do the second part of the first lab. I mentioned this last time, that the first part, and if you were able to do your design on Vivado for both the SOP and the POS output, well, part two is just adding a third output, which is going to be the NOR. So if you have your SOP and your POS working, you just got to add that third output, resim it to make sure that the simulation is still good. Now, remember again, because these different forms are logically equivalent, right? They come in from the same truth table. All your outputs should be in sync. So, when you look at your simulation, once you have those three outputs, you should be getting the same for all three. Your SOP, POS, and your NOR should be getting the same timing diagram, the same truth table. Okay, once you have that, you would download it to the board and demo it on the proof. Okay? All right, so that's sort of the game plan today. So let's start with universal gates. And what's meant by a universal gate is that you can make all other gates using a universal gate. So like I said, two of the gates are universal, the NAND and the NOR. And that's because I can make a NOT with the NAND, I can make an AND with the NAND, I can make an OR with the NAND, and I can make a NOR with the NAND. You can also make a NOT with a NOR, an AND with a NOR, an OR with the NOR, and also an AND with the NOR. Okay. You see the other gates, you can't do that. Like an AND gate, there's no way to make all the other gates with an AND gate because it doesn't have the inversion function. You need that inversion function in order to have a universal gate. Okay, and I'll explain why. Being able to do this, essentially being able to make a logic circuit all with one gate. I'll explain later, why that's useful. Okay, but right now, I just want to show you how you can do this. Okay, so in order to understand this, you first need to start with the truth table of a NAND, right, which we talked about earlier in the quarter. Okay, so here's some review. How would you fill out this truth table?
1, 0.
Yeah, which one's 0?
The N, both A and B.
A and B both go
at 1, 1.
Yeah. Right. Remember, with the NAND, you only get a 0 out when all the inputs are 1. Okay, otherwise you get a 1 out, right? Because remember, a NAND is equal to an AND and NAND stands for not in, right, where the not is on the output. So, an AND gate will give you a 1 out only when all the inputs are 1, right? And NAND only gives you a 0 out all the inputs are 1. Okay, so there's actually 2 different ways that I can use a NAND gate to get the not function. And what do we mean by the not function again? Right. A not gate just gives you the opposite at the output of what you have at the input, right? Okay, well, one way that I can make a NAND gate into a not gate is by looking at this truth table. Can you see that if I just look at these 2 rows, right? Just ignore the middle 2 rows. Just look at this first row and just look at this last row. If there was some way that I could make both inputs to a NAND gate the same, right? Either both 0 or both 1. Well, look, the output would be opposite what the input is, right? Because when both inputs are 0, I get a 1 out. When both inputs are 1, I get a 0 out. Now, this is where circuits, having some circuits knowledge helps. Okay, again, not required, not going to be tested on circuits. But those of you that had circuits, how could I make 2 inputs the same value, either 0 or 1? And remember, 0s and 1s just represent voltage level, right? 0 typically represents 0 volts, 1 typically represents some plus amount of voltage. So if I have a circuit and I want to make like 2 nodes the same voltage, what do? Short them. Yeah, connect them together, right? Short them together. So you see, one way to use a NAND as a not is you just take a NAND gate and you connect the inputs together. Okay, this is A and B, and I just physically connect them together. Like put a wire and connect them together. Because if I connect them together, they're going to have the same voltage. They're going to have the same value. So either A and B are both going to be 0 and I'll get a 1 out, or A and B are both going to be 1 and I get a 0 out. So you see, that's a NAND gate as a not gate. It's giving a not function. Okay, so any questions on what I did there? Again, if you had circuits, I think it helps with the understanding. If you haven't had circuits, just know when you connect 2 inputs together, they got to have the same value. Once you connect them together, there's no way one could be 1 and the other could be 0. Okay? All right, well, there's another way that we can make a NAND gate into a not gate. And the other way is by looking at this truth table, but only looking at the bottom 2 rows. So if I take this truth table and sort of divide it in half, let's say, and just ignore the top 2 rows, and just look at the bottom 2 rows. Can you see if I look at the bottom 2 rows, if I make one of the inputs of a NAND gate equal to 1, like I physically connect it to a 1. In a circuit, I would physically connect it to some plus voltage, like plus 5 volts. Can you see that we have inversion between the other input and the output?
Yeah.
Right? Because see, if I make one input to a NAND gate a 1, well, the other input is the opposite of what the output's going to be. Right? So you see, if I did this, if I took, it doesn't matter whether it's the A or the B. Okay. You see, if I did that, if I just took one input to the NAND and connected it to a 1, I'm going to get inversion between the other input and the output. So that's another way to use a NAND gate as a not gate. Okay? All right, well, let's move on. Okay, again, if you have questions, please ask. But let's move on and see how we can use a NAND as an AND. Okay. Well, I said earlier, and earlier today, and also we talked about this last week. We call it an AND gate because it's not AND, right? It's equivalent to an AND with an inverter on the output, right? So, when you see this symbol, this NAND gate symbol, you can think of this symbol as being this, that there's an AND with an inversion, a NOT gate on its output. So what do you think we could add to this NAND gate to make it an AND, to effectively get rid of that inverter at the output? Because if I somehow neutralize this inverter at the output, it would leave me just with an and, right?
Version
Not.
Yeah, where would I put it?
at the end.
At the output,
In series.
right, at the output, right? And what would I specifically put there? What would I draw?
Another NAND.
Another NAND.
Man is not.
Yeah, either this or that, right? So if I did this, right? If I took a NAND and I put out the output, a NAND that's acting like an inverter, this together is going to give me an AND, right? Because this NAND acting like an inverter is going to cancel out, effectively cancel out that inverter at the output of the NAND. I end up with an AND. Right? So you see a NAND with a NAND as an inverter at the output is equal to an AND. Does that make sense? Yes. All right. Okay, let's move on. Okay, this one. Using NAND to represent OR. Now, this is where your knowledge of De Morgan's comes into play. So yeah, I told you there was going to be a review, right? Remember De Morgan's? What does De Morgan's tell us that a NAND is equal to? Can you take pictures of that handout? Remember I had that handout with all the different identities and laws. Actually, there's a few extra ones on the table over there. If you...
It says that not A and B, not A or not B.
Okay, so yeah, it says a NAND is equal to what you just said, that not A, not B, or together. So how would I draw that as like symbols, you know, logic symbols?
Or the top string.
Okay, or okay, yeah, or with inverters on the input, right? So that's what that's one part of De Morgan's, right? Remember, the other part of De Morgan's is a NOR is equal to an AND with inverted inputs. Okay, but De Morgan's tells us this, that, you know, if I draw this symbol, I can think of it like this. I can think of it as this being equal to this, an OR gate with two inverters, or, you know, the inputs inverted. So how can I make this into an OR? What would I have to add to make it an OR? Because this is equal to that, but I just want the OR part. Put inverters on the input, right? Because that would neutralize these inverters. So you see, if I take a NAND and put let's see, we'll use the other way. We'll do this one. I could do this one too for all of this, but maybe I'll do one like that, and the other one I'll do with the inputs connected. Show the equal. Okay, so you see, if I take a NAND and I put inverters on the input, each of the inputs, that makes this into an OR. See, that's the OR function using only NAND gates. Okay, that's probably I think that's the trickiest one because you got to understand De Morgan's. All right, well, if you understood this, and you understand the difference between a NOR and an OR, because what's the difference between a NOR and an OR? Right, the NOR has an inverted output. So you just told me, or we just figured out, that these NANDs here give me an OR. So what would I have to do now to only use NANDs to get a NOR? Yeah, just take this and put an inverter on the output, right? Before NAND gates, right? So I would just take this. Just repeat what we had up here. Right, but then we'd add another NAND gate as an inverter at the output. So you see those four NAND gates give me a NOR. All right, so you see, I can take any circuit and turn it into, well, any circuit that has ANDs, ORs, NORs, you know, all the gates we talked about thus far, and turn it into a circuit that only is made out of NANDs. Now you might wonder, okay, so what? Right? What's the big deal? Well, you know how we talked about, one of the advantages of knowing SOP and POS is that, depending on what truth table or K-map you have, one form could give you less gates than another. Well, that's still true, but now knowing that I can take an SOP or a POS equation and I can just use one type of gate, just NANDs, or you're going to do as an activity show that you can, do the same thing with just NORs. Well, now if I have a logic circuit that I can just use one type of gate to make, that can make several people happy. Okay, now this isn't as true as it used to be back in the day. Okay, back when I was taking a class like this, and even up till about maybe 20 years ago, which again, I realize is your whole lifetime, that me, it's not all that long ago. This was more important. Nowadays, it's not as important because we have these ICs, like these basis boards where you can program and just select out what you need. But you see, back in the day, before we had these programmable ICs, typically, if you wanted a particular gate, you would have to get an IC that only had that gate on. Like you would have an IC that just had OR gates, or you would have an IC that just had NAND gates, or you would have an IC that just had inverters. Well, if you could do everything with one gate, it made your purchasing department, wherever you're working, very happy, right? Because they could buy just NAND gate ICs in bulk and get a really good price. Right? And that made marketing people really happy because that would lower the price of whatever the product is. Okay? But even now, it's still important to know this concept because even though at the chip level, it's not as important because, like I said, we got these programmable ICs where you can just select out whatever gate you want with software. But at the silicon level, okay, at the actual silicon level inside the chip, it's still useful to be able to do all gates with just one particular gate. Now, this is where having some knowledge of how silicon circuits are made. Now, I know the EEs in their circuits one class, you get a little bit of manufacturing, right? They talk about, like, there's that Silicon Run video. Did they not show that anymore? How many EEs in this class? Did you take 113? EE 113, the first circuits class. Did they talk a little bit about manufacturing? And... Oh, okay, yeah. Okay. I don't think the CPGs get that anymore. I don't know. Maybe they do a little bit in 115, I think it is. But, the more you know about how ICs are actually manufactured, you would see that it's useful to be able to do everything with one gate. Because basically, it would be one image as opposed to several images that you have to use to, fabricate that silicon circuit. Okay? So it'd just be more efficient and less cost. Okay, so that's universal gates. Like I said, I showed you the NAND here. Part of the activity today is you're going to do the same thing I did for the NAND, but you're going to use the NOR. And I put the truth table up here for you just so you could look up here if you didn't have it handy somewhere. Okay? All right, so before we move on and talk about NAND, NOR, do you have any questions up to this point? Okay, so let's go ahead and move on. And let's look at this equation here. This is something we did earlier, right? This was like the second day, I guess, when we had that truth table, my appetite for, what was it, chips, eggs, and salsa. And we came up with this SOP equation here, right? Because I would eat if there's eggs, I would eat if there's eggs and salsa, or chips and salsa. Okay. All right, well, a little review here. What is the logic circuit, the digital logic circuit? The diagram of gates. What is it going to look like since this is SOP? Like, what kind of gates do I have? A bunch of ands and one. Yeah, how many ands would I have? 4. I have 4 because each one of these terms, the inputs are being ANDed together, and then the outputs of those ANDs would go into an OR. So, it would look, I'm not going to draw the whole thing out. I'm just going to draw gates because we did this earlier. Again, this is just review. 3 inputs. You could fill it out, the rest of it, but the main thing is, in SOP, you're gonna have, you know, a number of AND gates, the same number of terms, and then that's all gonna feed into a single OR gate that ORs them all together, right? Okay, talked about that, everybody clear on that? Well, what I'm gonna show you next is I'm gonna show you how we can convert this SOP equation into a NAND equation, okay? So the first thing we would do in order to do this is we would double knot each side of the equal sign. So I double knot that side and I double knot this side, right? Because if I double knot, I don't change anything, right? I don't change anything logically. So now, you double knot a variable, it becomes a variable, right? Because it's just like taking something and putting it through 2 inverters in a row, right? You just end up with the same thing at the output of the second inverter. So double knot E is just going to be E. Okay, but now I have this, right? I have these 4 terms, and I've got a double knot over those 4 terms. Well, if I just look at this knot, okay, the knot above it I'm ignoring, okay? I'm just looking at this bottom knot over these terms. What kind of gate is this? Because look, if I treat this as an input, this term here, if I treat all these terms as inputs, I got an input, ORed with an input, ORed with an input, ORed with an input, the whole thing inverted. That's a NOR, right? See, that's the Boolean. If you just look at the bottom bar and all the terms, that's the Boolean expression for a NOR. And what does De Morgan tell us about a NOR? The other part of De Morgan's? Equal to, right, a NOR, De Morgan's tells us, the other part of De Morgan's tells us a NOR is the same as an AND with inverted inputs. Okay, so again, I'm treating each one of these terms as an input. So I take each one of them, I invert it, and I AND it. Let's see, I'm taking each term, inverting, ANDing. If I make a mistake, please let me know. It's easy to miss bars up here. Take that, invert it, take this, invert it, take this, invert it, take this, invert it, and then they're ANDed together, right? So you see, we did with Morgan's to go from here to here. We're doing this part of De Morgan's. Okay, now remember the top bar wasn't part of it, so the top bar is still there. So look. After we double knot each side and we do De Morgan's on this part of the expression, look what we're ended up with. If you just look at this, just look at that term, what kind of gate is that? These are ANDed, the whole thing's knotted. That's a NAND. That's this. That's this. What's this? And then look, those NANDs are ANDed and inverted, the whole thing inverted. So it's that. A NAND. You see why it's called NAND? It's like a nested NAND, right? These NANDs are nested within a bigger NAND. So just like when you look at the SOP equation, right? These were AND gates and they were ORed together. Look, these are NAND gates NANDed together. So how would I draw this NAND diagram? The SOP, it's a number of AND gates into an OR gate, right? Because these are AND and they're all ORed together. Now we've got NAND that are NANDed together. Yeah, it's all NANDs. That's why they call it NAND, right? Each term is a NAND. each term is a NAND, and then the terms get NANDed together, right? Because the terms are at the outputs of these NAND gates, so it's just going to be all NAND gates. Again, you can fill in the inputs. Everybody see what we did there? Can you see another way we can get the same result without bothering with the equation and just looking at this diagram based on what we just talked about over there?
Put all the NANDs in and get out the double line.
Yeah, exactly. Wherever there's an and, let's see, where did we put it? Right, we said that a NAND as an and is a NAND with this NAND at the output, that's an inverter, right? So I could take each of these and symbols and replace it with this. And then I could do the same thing with the or, right? I could take the or symbol and replace it with this. And can you see if I do that, I end up with the same thing? Why do I end up with the same thing? It seems like there'd be more gates, right? Because each one of these ands is going to give me these two NANDs, and this or is going to give me these three NANDs. So how do I end up with the same number of NANDs right there?
Each NAND on the left-hand side has an inverter on the output. So if you combine that with the inverter on the input of the or
Exactly. Yeah, they neutralize, right? Does everybody see that? Or do you want me to draw it out? I will. I mean, you can do it on your own, right? If you took each one of these ands and you replaced it with this, and you take that NAND and replace it with this, can you see that the inverter NAND on the output of the NANDs acting like an AND are going to cancel out with the NAND as inverters on the input of the OR. Right? The NAND acts connected to the OR. So that's how you end up with the same number. Okay, so this was like, you know, the Boolean way of doing it, and then there's like the diagram way of doing it, but you end up with the same results. Okay. All right, so any questions at this point? Because if there's not, I'm going to move the camera and we'll talk about NOR. And if you understood this, you're going to see NOR, same concept. Okay. All right, let's move the camera. Whoops. Let's see, we got to put this. Good. Okay, so let's move on here. And what type of expression is this? This again is from that example we did earlier. POS. Right, that's the POS, right? Product of sums. And just as a review, what are the steps that you need to do in order to get POS for E? Like, where do you start? Inverted. Well, let's say, well, I mean, it can be a K-map or it can be a truth table, but like what equation are we going to start with if we want POS for E?
That's what I mean, SOP time.
Okay. Yeah, whether you take it from a K-map like you're saying, or whether we did a truth table, right? Because remember, the only difference is from a truth table, it's non-reduced, right? From a K-map, it's reduced. So generally speaking, you start with SOP for not, right? If you want POS for E, you got to start with SOP for not E, because remember we said after we do the steps that you're going to tell me, everything inverts, ands to ors to ands, right? Okay, so you start with the opposite of what you want, right? The SOP opposite of what you want for POS. And then do you remember the next step?
you invert the inputs and switch hands to or
Well, that's going to be the end result, right? Is that everything inverts, ands to ors to ands. But I'm talking about the steps of the derivation that I did in class. Like the first thing was this, but then what did we do next? Yeah, you're not both sides. Not both sides are equal. Okay, and then what do you do?
Apply the Morgan.
Yeah, the Morgan's how many times? You just do it once like we did here?
I do it twice.
Yeah, you gotta do it twice. So yeah, the Morgan's twice. So the Morgan's times 2. So yeah, these are the steps. I mean, if you go back and you look at your notes, or if you watch the video from, I don't know, this last week sometime, you would see that's what we did. Okay? And you know, you do these steps and you would end up with the POS for E like we have right here. Okay, so now some more review. What is a POS circuit diagram going to look like? This is what it looks like for SOP, but what does it look like for POS? Exactly, right? Because each term is ORed together, so you're going to need an OR gate for each term, but then the terms are ANDed together, so the outputs of those OR gates all feed into a single AND gate. So it's just the opposite of SOP. Right? POS, you have inverters, or excuse me, OR gates. And they feed into a single AND. Okay. Okay, so again, it's just the opposite of an SOP, right? SOP, multiple ANDs into an OR, POS, multiple ORs into an AND. Okay. All right, well now, we're going to take this POS equation and turn it into NOR. Okay, and the way we would do that is you double knot both sides. It just becomes E. And now looking at this expression here, I'm just looking at the bottom bar and what's below it. Again, I'm ignoring that top bar. So look, if we take this as an input, right, all these terms as inputs, this input is ANDed with this input, is ANDed with this input, is ANDed with this input, and then everything's inverted. The whole thing's inverted. So what kind of gate is that? You're ANDing and inverting the whole thing. Yeah, that's a NAND. So you see, this is a NAND. And what does De Morgan tell us about a NAND?
Or with inverted.
Right, or with inverted input. So I take each one of these inputs, right, these terms, I knot them, and then I OR, right? So you see I'm going to take this. Invert the whole thing, and then OR it. Let's see, OR it. Inverted. Or it with the next one that's inverted. Lost track here. I'm thinking this. Oh, did I made a mistake here? You didn't tell me I made a mistake here. So let's fix that. How many people noticed and didn't tell me? How many people don't like raising their hand? Probably the same people didn't tell me. Yeah, if I make a mistake, please let me know. That's what threw me off. I was going along, I'm like, wait a minute. Okay, so here we go. Let's get back on track. You're just testing me, right? You wanted to see if I could find it. Okay, so we took each one of the inputs, we inverted them, we ORed them together. That's this part here. We still get the bar over everything though, remember? So you see why this is called NOR? Because look, you have a NOR here, 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 and then those NORs are ORed together, the whole thing's inverted, that's another NOR. So do you agree this is going to be just like this circuit, but 5 NOR gates? So this NOR will be I NOR gate. Yeah, I'm not filling everything out, but you could put the, input values here, and you could put F here or E here for the output. Okay, but that's what the circuit looks like. Okay, so again, it's called NAND NAND because it's called NAND gates. It's NAND gates feeding into a NAND, and it's called NOR because again, it's all NOR gates feeding into a NOR. Okay, and you'll see that once you have for the activity. That once you have all of these gates as NORs, you'll see that you could also get the same diagram by plugging in the equivalents of NOR for an OR and a NOR for an AND, just like we did in this case. Okay, so that's something you could do. I don't think it's part of the activity, but that's something you could do if you just wanted to prove it to yourself. So, there's basically two ways you can go from SOP to NAND NAND and POS to NOR, right? One way is the equation way, the other way is, the diagram way, using what you know about universal gates. Okay? All right, so any questions up to this point? Okay, because now we're gonna get to something that's a little bit more challenging. Okay, I don't think it's overly so. But you see, if you want to go NAND NAND to SOP or the other way, or NOR to POS or the other way, it's fairly easy. Now, of course, when you're first learning something, I realize nothing's really that easy when you're first learning it. But, it's really not that bad, right? Because to go SOP to NAND NAND, just doing the Morgans once, I mean, it was easier than this because you had to do the Morgans twice, right? I mean, if you look at it that way. And, if you want to go from POS to NOR, again, you're doing De Morgan's once. Okay. Also, can you see, if we go back to what we started with, I'm going to erase this since we're done with this. You look at what we started with, right? We started with this SOP equation, and you look at what we ended up with, right? The NAND NAND. See, a quick way to go NAND NAND the SOP, look, you just take what's underneath all the bars and just form them together. I mean, you're essentially doing De Morgan's again once going the other direction. Saying a NAND is equal to an OR with inverted input. But I mean, even if you didn't know that, if you just look at what's underneath all the bars, right, and just form them together, you can quickly go from NAND NAND to SOP. And likewise over here, you can quickly go, again, if you go back to what we started with. And if you look at this NOR and compare it to what we started with, again, if you just take the terms underneath the bars and AND them together, you can quickly go from NOR to POS. All right, so you see, going either direction between these, relatively, at least compared to some other things we've done, not that bad. All right, but if you want to go NAND NAND to POS, or if you want to go NOR to SOP, it requires a little bit of work. And it actually requires some of the things we talked about earlier in the quarter, like a K-map. Okay? So let's go ahead and do that. Let's go from NAND NAND to POS. Okay? And we're going to use this example. Well, just like I said a moment ago, you can quickly go from NAND NAND to SOP. Because again, all you have to do is take the terms underneath all the bars. So this would be SOP for F. I just take the terms underneath all the bars. So I take AC and you just form them together. And I would take not CD. And I would take actually, did I forget a bar here? Yeah, I forgot a bar here. So I made another error. Sorry about that. There should be a bar because it's NAND. Let's see. You understand why I'm missing that bar, right? Because it wouldn't be Nan if that bar was, sorry, that was a mistake on my part. Yeah, so you see, I went from Nan to SOP by just taking the terms underneath all the bars. Okay, everybody see what I did there? All right, so now here's something we haven't done before, because the next thing I would want to do, because see, since I want POS, once I have the SOP, I have to either go through a truth table or a K-map to get the POS, right? And here I'm using a K-map because since you know what K-maps are now, you know, usually in a practical sense, you always want the reduced equation, right? Even if it's not asked for, usually that's what you want, okay? So last class, you know, you had a K-map, and then from the K-map, you would get the reduced expression. Here we have an expression, and we want to put it into the K-map. So it's like we're doing the reverse. Okay, but you should be able to go both directions. Right? You should be able to go both directions, right? So since this is SOP for F, when I take each term and I write the grouping for each of the terms in this K-map, since it's SOP for F, what am I going to be writing? Am I going to be writing groups of zeros or groups of ones? Ones, right? Because it's F. Okay. So let's look at this term by term. Let's look at this AC term. That AC term came from what grouping of ones? First of all, how many ones had to be in that grouping since it's a 2 variable term for a 16 cell map? Four, right? It's got to be a grouping of 4. So what 4 cells did that AC come from?
14, 11, 15.
Again, you said what?
15, 14, 11.
15, 14, 11. All right. People agree?
Yeah.
How many people agree? How many people don't agree? How many people don't like raising their hand? Why'd you raise your hand then? No, that's right. Because remember, the term comes from what's common to that grouping, right? So these 4 ones, right? They're all in the A rows. They're all in the C columns, right? See, what's different is B and B bar, so that drops out, and also D and D bar, so that drops out. So yeah, AC came from that grouping of 4 ones. Okay, how about not C, D? Where am I going to put the ones for that? 1, 5, 13, 9. Okay. Everyone agree? Yeah, because those 4 ones, they're in the not C column and also the D column. Okay, then we have not A, B, not C. So since this is 3 terms, what number of groupings do we have? Just 2, right? So what 2 cells give us not A, B, not C? 4 and 5. 4 and 5? These 2, do everyone agree here? It's in the not A row, not C column, and not U or B row. All right, so does everybody agree that this equation came from this K-map, right? See how we went reverse? But when you go reverse, you still got to think the same way as when you're, you know, circling the group, because like we did last class, right? It was last class K-maps, right? Yeah, Thursday. Yeah. Okay. All right, so what do we do with the rest of the cells? Yeah, you put in zeros, right? Zeros. So did I get all the zeros? Okay, so now, since we want POS, so this is more review, right? We want POS for F. So to get POS for F, you need SOP for not F, right? SOP for not F, right? Because once we have SOP for not F, you know, the derivation is here. But again, what ends up happening is everything gets inverted, ands to ors to ands, right? So since we want POS for F, we got to get SOP for not F. And we're gonna use this Kingman, right? We're getting the reduced SOP for not F. So since I want not F, what am I interested in circling now? Zero. Remember, not F comes from zeros, right? Whether it's a truth table or K-map, it comes from zeros. All right, so what would you group first?
4 from the top.
Right, if you take this group of 4. And what term is that group of 4 going to give us?
Not AC.
Not AC, right? Yeah, everyone agree? Is right there. That 4 grouping, it's in the not A row, it's C column. So this is going to be not AC. Okay, let's see, what would you do next?
2, 9, 0. Or sorry, 8.
Okay, you can do 8 and 0. Okay, it looks like there's more than one correct solution. Okay, but anyway, 0 and 8, what term is that going to give us?
Not B, not C.
You said not B, then what?
Not C. And not.
Does everyone agree? Let's see, it's in the not C column, not B rows, and not D column, right? It's only A that's different, right? So that drops out, right? Because this is in the A row, that's in the not A row. So whatever is different, right? That drops out. All right, and then how would you take care of this last 0?
You just do 12 and 8.
Right, 12 and 8. Because remember, you can overlap. 12 and 8. So what term would that give us? 12 and 8. Say it again.
A, not C.
A, not C. So let's see. Yeah, they're both in the A row, not C columns, not D. Yeah, the only thing that's different is D. So, yeah, so you could have another solution because, you know, instead of grouping 0 and 8, like you could still do this 8 and 12, and then you could have done 0 and 2 grouping, right? So there's 2 correct reduced expressions for this particular example, okay? But now since you have SOP, well, once you have SOP, like we did here, you can go to NOR if you wanted to. I just went to POS here, but once you have POS, you can then go NOR by doing De Morgan's once like we did here. Right? So, you know, if you went one more step, and I'll leave that for you to do on your own. Okay, but you would just repeat what we did here. You just do De Morgan's once. Well, you double knot, then do Morgan's once. But yeah, remember, once you have POS, it's just what we did here to go NOR. Okay? All right, so any question on what we did here? Again, the big thing is that to go from NAN to POS, you got to go through either a truth table or a K-map.
You haven't gotten the POS yet.
Oh.
Yeah.
I'm sorry. Sorry about that. Yeah, we got to go to POS. POS. So what do we do? This is review, right? Yeah, De Morgan's twice. So what's, you know, well, you knot both sides, then you do De Morgan's twice, and then effectively what happens?
You get inverted inputs and yeah.
Well, everything inverts, yeah, even the output, and then what else? Everything inverts, and the OR states. Yeah, thank you for pointing out a big mistake there. It's getting ahead of myself. So it's going to be like this, right? I always double check because it's easy to miss a bar. So everything inverts. Right, so did I invert everything? We did. Yep. And then ands the ORs, and then the OR station. Right. So everybody agree that's right. So now you can go from this to NOR. But thank you again for pointing out my omission. Okay. All right, I know we're at the top of the hour, but we just got this one more example. This should take about 5 or 10 minutes. So if it's okay with everybody, I'll just plug on instead of taking a break. Is that okay? Okay, so what's that?
Camera.
Oh, camera, yes. Thank you. All right, just gonna, I think I can go much closer, so I just have to aim it that way. Okay. All right, so now let me show you how to go nor to SOP. Again, nor to POS is just what we did over here, right? It's the Morgan's, but you go nor to SOP, you got to go through either a truth table or a K-map. So here's our example. And like we showed here, if you look at nor compared to POS, you're just taking the term underneath all the bars and then anding them together. So you see, I can quickly go. Break this in. I can quickly go to POS for F by just taking what's underneath the bars and anding them. Okay, so everybody see what I did there? All right, so now I want to go into a K-map. And remember, we're trying to get SOP. Right? We're trying to get SOP this time. So when you have a K-map and you want to get SOP, you're looking at what? Are you looking at zeros or ones? You're going to look at ones, okay? Now, we have POS for F. And, you know, just like we talked about last week, that it's easiest to go SOP to a truth table or truth table to SOP. And also, it's easiest to go SOP to a K-map or a K-map to SOP. So here I have POS for F. But before I want to go in this K-map, I just want to make that SOP, right? Don't you agree? So when I make this SOP, what's going to happen? And anytime you go POS to SOP or SOP to POS, what always happens?
The thing gets split, so you're gonna have not have.
Yeah, everything flips, ands to ors to ands. So you see, when I make this SOP, it's going to be SOP for not F. Right? Then I'm going to have not A, not C, and then B, not D. Right? So I'm just doing the, you know, though we not each side do the Morgan's twice that we've shown before, right? So you see everything inverts, ors to ands, ands to ors. So everybody agree that's is what I would get? No mistakes. So this is what I want to put into the K-map. And since it's not F, it's going to be groupings of what? Four groupings of zeros. And over here, right, it was SOP for F, so it was groupings of ones. Here it's SOP for not F, so the groupings are going to be zeros. So what grouping am I going to have for not A, not C? 0, 1, 4, 5, and what am I going to put in those cells? Zeros. Yeah. Right? That would be for the not A, not C term. Okay, now how about B, not E? Well, let's say you said 6, 14, 12. All right, and then 4, but it's already 0. Okay, so let's see. That would give us E, not D. Everybody agree? Right, because that 4 grouping, they're all in the B rows and also in the not D columns. All right, so what goes in all the other cells? Ones. So now I would come up with SOP for F by grouping the ones. All right, so how would you group these ones?
I'd start with A, not B.
Okay, what cells?
That's 8, 9, 11.
Oh, so this row down here?
Yeah.
All right, do that row. What did you get for the term?
A, not B.
A, not B. Everybody agree?
Yeah.
All right, what do you do next?
A, B,
Okay, what cells?
13, 15,
Yeah, this group of four. 'Cause again, you can overlap groups. And what term did you get?
A,
AD, yeah. Everybody agree? All right, what's next?
CD,
Yeah, CD.
3, 7, 13, 11.
Yeah, doing this column here. Right, that would give us CD.
I'm gonna do not B, C, which is 3 to 11.
Oh, okay, yeah, see, actually, I missed that. I was looking at, I thought you would just do this, but yeah, we can, because these edges touch there. We got another four group. Yeah, very good. I didn't see that right away. See, sometimes you gotta be really careful with these. It's easy to miss. But yeah, we got another four grouping. Everybody see that? Because remember, the top and bottom touch, the edges touch, so you can go across edge. So, okay, so what term are we gonna get here?
Not B, C.
Yes, not BC. Not BC. Not BC. Right? Yep. All right. And then, since this is SOP, right, you can use what we did here to go to NAN. Oops, over here, sorry. Since this is SOP, just like we did here, you can go from SOP to NAN if you wanted to go another step. Okay, so I know this was a lot of stuff today. Again, what's new is what is meant by universal gates. Okay, that was new. And then also what was new is NAN and NOR. All the other stuff, I know there's a lot of stuff, but I would say half of it was review. You know, review of things we talked about previously. Okay, so I think this is a really good lecture as kind of like a litmus test that, you know, if things were making a whole lot of sense at the board here, I would say you're in really good shape up to this point. If, you know, some of the review stuff we were talking about is still a little shaky, you know, then you might have to put a little bit more time to make sure, you know, you got a good grasp on that, okay? All right, so for the rest of today, and if you want to take a break, you know, at any point, that's fine. But for the rest of today, you know, there's the activity. Again, there's two parts of the activity. One part is doing what I did here for the NAN, for the NOR. And then the other part, well, both parts are on a handout that should be at your table. There should be enough for everyone to have their own. If not, let me know. And then the answers are up on the wall over there. And then once your group passes in the activity, the last thing to work on today is the lab. And you can finish it now, right? Because the third output that you want is a NOR. You already, if you did part one, you already have your POS. So all you have to do is take your POS and do what I did here to get your NOR, and then just add that to your design. Okay?